Okay, for this video, we're going to be combining all of the tools that we've learned so far, which has to do with translation and truth tables um, and categorical logic generally. So now what we're going to do is we're going to take our connectives that I've all written across the board here, and we're going to learn how these connectives function when we give them truth operations with regard to truth tables. So truth tables were invented by Ludwig Wittgenstein, early 20th century, mid 20th century, student of Bertrand Russell, who protested World War II, famous logician. And they're a really helpful tool for the way in which we can come to understand what will make our everyday sentences true and false, given the way that they're constructed logically and the way that we symbolize and break down the logical contents of those sentences. And so there's some basic formulas here. And the one that we're going to start with is the connective for negation, which is not, right? So when I'm constructing a truth table, it's important that I notice how many variables, letters, sentence letters, that I'm utilizing in the construction of the table. So we have a general rule for this, which is the 2 to the nth power, which is where n stands for the number of sentence letters that appear, different sentence letters that appear in the truth table. So you can have multiple iterations of a sentence letter. So for instance, either I go to the park, or if I go to the park, then Andy likes barbecue chips. So what I've done is I've used the same sentence letter, which would be represented as either I go to the park, or I go to the park. If I go to the park, then Andy likes barbecue chips, which would look something like this, right? So here there's only 2 unique sentence letters. And because there are only 2 unique sentence letters, I would only need to plug in a 2 here, which means that 2 to the second is 4, and so I'm going to need 4 different truth values for any truth table containing 2 unique sentence letters. Now, for our negation, our truth table only has 1 unique sentence letter because the negation is a one-place variable. So when I plug in a 1 here, I get 2 to the first power, which is just 2, which means that I need 2 different combinations of truth values, which I'll write as true and as false. And the operation of the negation on our sentence letter is that it flips the truth value. So if P is true, then not P is false. So if it's true that that it's raining right now, it would be false that it's not raining. And likewise, if it's false that it's raining, then it's going to be true that it's not raining. Okay, so what a negation does is it flips the truth function, or the truth value of the sentence letter. Okay, so here's where it gets a little more complicated, is when we now have 2 unique sentence letters in our truth table. So again, I'm going to plug that into our equation here. So 2 to the second is 4, which means that I'm going to have 4 different lines on my truth table. And there's a formula for this. You can, again, brute memorize it. You can read the book. I think it explains sort of the motivation for doing this. But what I'm going to do is I'm going to write true, true, false, false. And this is 4 lines, but it's only for one of my sentence letters. So for the next one, I'm going to write true, false, true, false. Now you'll notice what I've done here is I've gone from 2 at a time, true, true, false, false, to alternating, true, false, true, false. The reason that I've done this is that what I want the truth table to do is to represent every single truth value that's possible for the combination of 2 sentence letters. So alternating in this way by doing 2 and 2 and then 1, 1, 1, 1 gives me this. So either both of our sentence letters are going to be true, likewise they'll be false. The first one could be true and the second one false, or the first one true and the second one false. And this exhausts all of the possibilities for truth values for these two sentence letters. Okay, so now what does the conjunction tell us with regard to truth values? Well, a conjunction, this operation is only going to be true when both of the parts are true. So if P is true and Q is true, then the sentence P and Q is true. But if one of them is false, then the whole thing is false, so that makes these false. And now these are both false, so that's no good either. So this is what our truth table looks like for conjunction. The conjunction is only true when all of its parts are true. So say I had P and Q and R. We're not going to do truth tables for 3 sentence letters, but this is just a helpful illustration. So if P and Q, then R here is only true when P is true, when Q is true, and when R is true. So the whole thing would be true. But if any of these parts were false, that would make the whole thing false. And we see that in our truth table right here. And now let's do disjunction. Again, I'm going to write my variables. So for the first one, I'm going to do true, true, false, false. And for my second one, I'm going to alternate true, false, true, false. And again, this exhausts the limit of possible truth combinations for this sentence. And now, what does the disjunction tell us with regard to truth value? Well, it tells us that anytime one of the two sentence letters is true, then the statement that conjoins them as a disjunction is true itself. So this says that both P and Q are true. It only needs one of those statements to be true, so of course one of them is true, both of them are, turns out. So that's true. In this case, true or false, one of the sentence letters is true, being P, and then when Q is true but P is false, again we have one true statement. But in our last line where both P and Q are false, we have no truth at all, and so it's false. And you can think about this as saying either it's raining or it's sunny. If it's false that it's raining, it's not the case that it's raining, and it's also not the case that it's sunny, then my statement, either it's raining or it's sunny, is false. But if it's raining and it actually is raining and not sunny, then it's true, and likewise the other way around. Similarly, if I said either I'm recording a video right now or I'm giving a lecture, both of those are true, so the statement is true, which we call the inclusive or. An or is not disjunctive unless it's stated that way, but for the purposes of this class, you can always consider the or as inclusive, that just so long as one of the variables is true, then the whole thing is true, including if both are true. Okay, so let's do our implication or our material conditional, the conditional. So again, true, true, false, false, and true, false, true, false. Okay? Now, this one is weird. It's its own thing. It might require brute force memorization at first. If you get into a more advanced logic course, you'll learn some of the philosophical problems with representing a material conditional in the following way. Although it is the classical way in which the conditional has been represented, there are many objections to it that are out there that philosophers and logicians have developed their own unique logics to in virtue of this very elementary and basic representation of the conditional as we use it in our everyday language. But again, for the purposes of this course, it's okay to, and in fact, it's all that will be required and expected is just knowing what I'm about to show right now. So the conditional, the way that I think about the conditional when I'm looking at this truth table is that there's only one place in which the conditional statement is false. And that is when you have a line that has a true antecedent and a false consequent. That's when it's false. And this is the kind of statement that says, if it's raining outside, then the ground is wet. And what the truth values of this would say was P would be if it's raining outside and Q would be it's wet. It's true that it's raining outside, but false that the ground is wet. that is a direct contradiction with the statement, if it's raining outside, then the ground is wet. The implication requires that the ground be wet if it's raining, given the statement. And so this is a contradiction. It just cannot be. And so the one line where our conditional is false is when there's a true antecedent, the first term, and a false consequent, the second term. And in the rest, it's true. If it's raining outside, then the ground is wet. It's raining outside and the ground is wet. We have a true implication. If it's false, that if it rains outside, that it's raining outside, but it's true that the ground is wet, our conditional can still be true. And if you think about it, here's why. Because there's other reasons given that conditional that the ground can be wet. It is not a sufficient condition for the rain that the ground be wet. Rather, it's a necessary condition that the wetness just attaches to rain itself. I could spill a bucket of water on the ground and it would still be wet. So even when the antecedent is false but the consequent is true, we can still have a true condition. And here's the weird line, where lots of deviant logics are developed in virtue of this line in particular, which is that if it's not raining outside and the ground is not wet, then the conditional is still true. This is kind of like a hypothetical situation. The conditional is hypothetically true, even though none of its, neither the antecedent nor consequent are true. This is like saying it's sunny outside, but it would be true that if it were raining, then the ground would be wet. So what we're doing is we're setting up a hypothetical conditional, and the world doesn't yet contradict that hypothetical conditional, and so we accept the conditional as true. Okay, now finally for our equivalence, our biconditional, our if and only if, finally true, true, false, false, true, false, true, false. Okay, so I've filled out my P's and Q's here. The equivalence, again, the way that I like to think about equivalence is where it's true, and so, sort of as opposed to the material conditional, the regular conditional, the horseshoe, which is I think of as where it's false. I think of the biconditional as where it's true. And a biconditional is only true just so long as both the antecedent and the consequent of it share the same truth value. So if they're both false or if they're both true. So, and again, this is the reason we call it equivalence, that an equivalence only holds if the truth values are the same on both sides, because otherwise they wouldn't be equivalent, right? So the two lines where our truth values are the same are the first and the fourth, which is where they're both true, they're both false. And so our statement, P if and only if Q, Q if and only if P, those can be reversed, that's just fine, are true here, and then they're false where the values of the antecedent and consequent of the biconditional are different, which would be lines 2 and 3. So here is all of our truth tables for our basic operators. These are your cheat sheet. This is it right here. This is everything that you need to know for this course about truth tables. Just looking at these statements, you'll be able to answer every question, like the two that I've written here as examples. These aren't exactly from the quiz, but they're really similar to the ones that I wrote. And what we're going to do is we're going to take these values from our truth tables in order to determine what the truth value of these two statements are. Now, it's important that we be given initial conditions. Now, these are our initial conditions, these first 4 lines here, and here, and here, and here, right? In order to be able to play with these examples. And our initial conditions are, let's accept that variables A, B, and C are true, and that variables X, Y, and Z are false. And so immediately what we can do is say we're given problem 1. Determine the truth value of this whole statement given these initial conditions, A, B, and C are true, and X, Y, and Z are false. Immediately what I can do is I can say, well, A is true, so I write a little T under it, and X and Y are both false, and that's my first line. Now, what I'm going to start doing is looking at the operators and the truth values that I have so far. So when I have a variable that's negated and it's true, then it takes the opposite truth value. So that would make it false. So this second line makes our true into a false because we're negating the truth of it. So it becomes false, right? And likewise for the conditional, our conditional, we're going to look at this truth table when both the antecedent and the consequent are false, which occurs here, our truth value is true. Now, our main connective is the biconditional, the equivalence statement. Now, an equivalence statement, again, is only true when both its antecedent and consequent share the same truth value. These don't. So our answer is false. That statement, given those initial conditions, is false. Okay, let's do question 2. It's not the case that if C, then Y. Again, A, B, and C are true, and Y is false. Our main connective is the tilde, because the tilde operates on the largest, has the widest scope. And now we have a conditional, a true then false conditional. Again, we're going to go to our conditional table, true then false. That's where it's false. And then we're going to negate this one. So anytime you negate a false, it becomes true. And we find that given these initial conditions, problem 2 is true. So this is our basic introduction to truth tables. Hopefully that was clear and helpful. And hopefully you enjoy doing these problems. They're, in my opinion, they're super fun. I have a lot of fun with them. But if you're struggling, if you're having any problems whatsoever, please don't hesitate to reach out and ask for help. I'm happy to answer emails or meet in person or offer whatever I can to help understand this stuff. I recognize that it's a lot of T's and F's and a lot of letters and different ways of thinking. It's stretching new muscles for those of you who haven't done this before. But these are really important muscles to be stretching. They're muscles that help you. Once you memorize this stuff, it implants itself in your brain so that as you're thinking and working through problems, as you're writing papers, as you're going through your everyday lives, you'll have a little tweak in the back of your head that says, does this really hold? Is this true? Is the implication that I'm making consistent? Is it logical? And does everything really fit together as I think it does? And that's a really important and helpful skill to have. So this stuff is important, but also new and confusing and different looking than anything you may have seen in the past. So again, I'm happy to help how I can. If you need it, reach out, please. And that's it for this video. Thanks.